Good evening. We are now going to start with the sixth chapter, Electromagnetic Induction, in our NCERT textbook. We started with the first two chapters dealing with charges at rest, electrostatics. We went on to moving charge, meaning charges moving in a conductor, producing what you call as current. In the third chapter, current electricity. And then in the fourth chapter, we went on to discuss about how a current in a conductor can produce a magnetic field. And then in the fifth chapter, we dealt with the Earth's magnetism. And now in the sixth chapter, we're going to learn something that is reverse of what's happening in the fourth chapter. Like I told you, in the fourth chapter, we are talking or discussing about how current carrying conductors can produce a magnetic field. And in the sixth chapter, we are now going to discuss about how a change in the magnetic field can produce or induce a current in a conductor. So that's what's the reverse of fourth chapter is what we're going to learn in electromagnetic induction. How a change in magnetic field can induce current in a conductor. So before we start this chapter, we need to discuss what you might already know as magnetic flux. Because electric flux we already defined in the first chapter as the number of field lines passing perpendicular through a given area where we discussed as E dot delta S, where E is the electric field, which is the number of field lines passing through unit area multiplied with the whole area, and you have what you call as the electric flux. In a similar manner, now look at this. Suppose you have an area. Let's say this whole area is capital A. Now you will see that I've put dots here, and in the fourth chapter I already told you that if you see dots you are in an area, you are supposed to know that it represents a uniform magnetic field passing perpendicular and coming out, so that you are now looking at the north pole. Instead, if you look at an area and they've marked the magnetic field with cross like this, then you're supposed to know that the magnetic field is perpendicular to this area but going in, so that you are looking at the south pole. So whenever you look at cross marked as a magnetic field, please understand that they represent the south pole, because the magnetic field lines are perpendicular to this area and going in. Whereas if you see dots, you need to know that represents the north pole, because in this area the magnetic field is represented as dots. That means the magnetic field lines are perpendicular to the area and coming out. Okay. Now here I have marked a small square. Imagine this is 1 meter and this is also 1 meter. So that you may say that this is unit area 1 meter square. I have marked 4 magnetic field lines there. So the number of field lines passing perpendicular through unit area is what you call as magnetic field intensity B, which you already know, its SI unit is Tesla. The number of field lines passing perpendicular through the whole area is what you call as magnetic flux. So number of field lines passing perpendicular through unit area is what you call as magnetic field B, whereas the number of field lines passing perpendicular through the whole area is what you call as magnetic flux phi. So then we may write magnetic flux phi is equal to B dot A, both being vectors, and this is the dot product, so BA cos theta, where theta is the angle between the magnetic field and the area vector of this area. Now if this loop we are talking about has, let's say, total number of turns is N, capital N, then the total flux will be NBA cos theta. So flux is dependent on the number of turns in the loop, depends on the magnetic field intensity B, depends on the area, depends on the angle between magnetic field and area vector. Now here the SI unit naturally will be B dot A. So B is in Tesla and area is in meter square. So Tesla meter square is the SI unit of flux. It's also represented as Weber, represented as WB, Weber. So the SI unit of flux, magnetic flux, is Weber, which is Tesla meter square. Okay, now Faraday and Henry did extensive experiments and discovered that whenever there is a change in flux through a loop, you can induce current in that loop. So change in flux will induce current in a loop. Michael Faraday and Henry did extensive experiments, and in your textbook on page 205, you have experiment 6.1, 6.2 and 6.3. I'll briefly explain to you what the experiments are. What Faraday's experiment was, is he first took a coil like this, a coil of n turns. I've taken a copper coil of 100 turns, and then keeping the coil fixed stationary, he used a bar magnet, whether the south pole or the north pole, he used a bar magnet. Now bar magnet, as you know, has field lines like this. You know that a bar magnet has, let's say this is north and this is south, has field lines coming out of north and entering the south pole. And at the poles, you know the number of field lines maximum number of field lines are there at the poles, and as you go away from the poles, the number of field lines will decrease. So what he did is, he took this coil, kept it stationary, and connected a galvanometer to this coil to detect current, and then he brought this bar magnet, the pole of the bar magnet, closer to the coil and kept moving in and out of the coil like this. And as you do this, what is happening is, as the poles come closer, the number of field lines will increase, because at the poles the number of field lines are more. So number of field lines entering through the loop will increase. As you pull it back, the number of field lines in the loop will decrease as the bar magnet moves back. So as he moved in and out, what happened is, he's actually changing the flux through the coil, and because flux is what? B dot A or BA cos theta. As you bring it closer, the magnetic field lines are increasing. As you pull it back, the magnetic field lines are decreasing. So as he kept moving it in and out, he was changing the flux. So as you change the flux, he found out that there is a deflection in the galvanometer, and that means there is a current produced in the coil without any other voltage source. There is no other voltage source except he connected a galvanometer. So then that current he called as the induced current, because that current is not from any voltage source. Instead, it is because of a change in flux. He also discovered that the faster the movement of the bar magnet, that means faster the change in the flux through the coil, greater is the induced EMF, therefore greater is the induced current. So EMF E is rate of change of flux through the coil, where flux is, so this is d by dt of NBA cos theta, where flux is NBA cos theta. This is the induced EMF, and the induced current in the coil is EMF by resistance of the coil. Same, Ohm's law, V by R. So any change in the flux through the coil, the rate of change of flux is what we have as induced EMF. Induced EMF by resistance of the coil will give you the current produced in the coil, which was detected by the galvanometer. Experiment 6.2 talks about two coils like this. He took two coils like this, copper, different number of turns or same number of turns. You can take two coils like this and connect a battery to a voltage source here, so that this coil carries current. If this coil carries current, then from the fourth chapter, you know it already has a magnetic field associated with it, like this. So what we have here is, we have two coils. One coil is connected to a galvanometer. We have a galvanometer connected here. Okay. And then to this he connected a source. Voltage source. So that this is now carrying current. This is now carrying current. Okay. So because of this, you know that all circular coils have a magnetic field along its axis. By Savat law, we derived the formula for that. Along the axis, magnetic field given by mu 0 I r square by 2 into r square plus x square the whole raised to 3 by 2. So along the axis there is a magnetic field, and because it is carrying current in the clockwise direction, we know that the magnetic field will be inwards like this. Okay, magnetic field B is given like this. So there is a magnetic field which is also now passing through this loop, because the two loops are kept coaxially like this. When the two loops are kept coaxially like this, the magnetic field due to this coil will also be passing through this loop or this coil. So we have the magnetic field because of the current in this loop passing through this one. Now what he did is, he brought this coil closer and moved it away, closer and moved it away in this manner. So this is kept stationary, the one that is carrying current, because of whom there is a magnetic field, and this coil is also experiencing the same magnetic field because it kept coaxially, and then he kept moving this coil in and out, which means as you move this distance x goes on changing because you are bringing it closer and moving it away. Okay, so now what happened is, as this magnetic field changes, we know that the flux through this is given by NBA cos theta. So because there is a change in B, there will be a change in flux, and because of a change in flux through this, there is an induced EMF given by d phi by dt, and there therefore is a induced current given by the induced EMF divided by the resistance of that coil. So that induced current will now deflect the galvanometer, and the galvanometer showed deflection. The third experiment that he did is the same pair of coils. He did not move it. Both of them were kept stationary, but this was connected to a key and then to the voltage source. As soon as he switched on the key, there is sudden increase in the current. Any increase in the current will increase the magnetic field that is passing through the other coil, and a change in the magnetic field here will again produce a change in flux through this coil, because of which there is an induced current, and the induced current will deflect the galvanometer. What he also noticed is that once he has closed the key and the current has become a constant current, then when the current is a constant current, there is no change in magnetic field. If there is no change in magnetic field, then the flux is a constant and d phi becomes 0. There is no change in flux. The flux is a constant. When there is no change in flux, there is no deflection in the galvanometer, which means that there is no induced current. So the induced current will last only as long as there is a change in flux. If the flux becomes a constant, then immediately the induced current becomes 0. What he then did is, he opened the key. As soon as he opened the key, the current in the coil decreases, and because of a current decrease, there is a decrease in the magnetic field of this coil which is passing through this coil too, and because of a decrease in the magnetic field, there is a decrease in the flux through this coil, and then there is a change. A decrease would also then mean a change in flux, and when there is a change in flux, there is induced current, and the galvanometer showed deflection, confirming that the induced current lasts only as long as there is a change in flux, and the induced current is dependent on the change in flux and the rate at which the flux changes. Greater the rate at which the flux changes, greater will be the induced EMF and greater will be the induced current. Okay. So that is Faraday's experiments that you need to know in the chapter. 3 experiments. Now we go on to derive an expression for motional EMF, that is EMF in a coil because of the motion of a conductor in a magnetic field. Now before that, we need to discuss what is Lenz's law. So Faraday's law is induced EMF in a coil is d phi by dt, that is rate of change of flux through the coil is equal to the induced EMF in the coil. Then we have Lenz's law. Lenz's law says that the induced EMF or the induced current should flow in such a manner that it always opposes the change in flux, because only then this will be under law of conservation of energy. What does law of conservation of energy say? You cannot create new energy, nor can you destroy energy. It can only be transformed from one form to another, changed from one form to another. So in a coil, you can't just produce current, energy, just like that. So it is energy in some form converted to electrical energy. So he said, you need to know that the induced EMF is always producing an induced current, which should only flow in such a manner that it opposes the change in flux. Let me explain this further. Why this negative sign? So here we have a coil. So this is a coil, okay? And I'm representing the coil like this, okay? So I have this bar magnet with the south pole here and the north pole here. So when my bar magnet is brought like this, you know, for the bar magnet, the field lines are coming out and then going in through the south. So we have the magnetic field lines from the bar magnet going in like this, okay? So this is the north and this is the south. The field lines are in this direction. Now, according to Lenz's law, the induced current in this coil must flow in such a manner that it opposes the change in flux. So as you bring this closer, moving closer, as your bar magnet moves closer, the number of field lines go on increasing. Flux is equal to BA cos theta. Here I didn't use N because there's just one turn of the coil that I'm using. BA cos theta. So as you bring this bar magnet closer, the magnetic field, number of field lines in unit area is increasing. Flux is also increasing. Lenz's law says that the induced current must flow in such a manner that the induced current opposes the change in flux. The change in flux is increasing. The induced current must oppose it. That means it should flow in such a manner that the flux decreases. So here, if the flux should decrease, then this induced current must produce a new field that is opposing this, like this. Okay? So that means this is not. So if you're looking at a coil like this, because of the bar magnet moving closer, the field lines are going in like this. That means the coil should produce a current such that because of the current, we have a new magnetic field that is coming out in this manner. So you should look at the north pole. So that means current can only flow in the anti-clockwise direction, because I brought my bar magnet closer to the loop. When I bring the bar magnet closer to the loop, the number of field lines entering the loop is more, because of which the induced current must try to decrease it. Decrease it means this induced current produces a new field that is opposite to this existing field. So since the existing field was going in like this, the new field must come out here like this, so that you will be looking at the north pole. North pole would mean the induced current can only flow in anti-clockwise direction. Okay, let us see what happens if this bar magnet is moved away. So the bar magnet is now going to be moved away. So this is our loop. So the bar magnet is moving back. The field lines are still going in the same direction. Field lines, here we have the north. I'll just represent one. So this is north. From the north, the field lines are going in and coming back to south left. So this is the direction of field lines going in. Now, because your bar magnet is moving back, the number of field lines here is decreasing. According to Lenz's law, the induced current must try to oppose that decrease. That means it should try to increase it. If the new induced current must increase the flux through the coil, it means it should produce a new field in the same direction. Right? So that means due to the bar magnet, this is north. The new field produced by the induced current also should have the same. So if you look at the case here now like this is a coil. You already have, this is the north pole, the black part is the north pole. So your field lines are actually going in, but you're pulling your bar magnet away. When you're pulling it away, the number of flux lines through the coil is decreasing. So according to Lenz's law, the induced current must try to increase it. Increase means it should produce a new field that is in the same direction, so that the two will get added up and it will increase, and therefore the new field also should go in like this. That means you're looking at the south pole. If you're looking at the south pole, then the current should flow in clockwise direction. So we have the south pole here. So when we look from this side, the current should go in the clockwise direction, because I already told you anti-clockwise would be coming. This will be north. Clockwise means you're looking at the south. Okay. So I hope that is clear to you. Now let's see how this is in accordance with law of conservation of energy. So in the first case I told you, we were bringing the bar magnet closer. We were bringing the bar magnet closer. So we have a coil here like this. This is a coil. The bar magnet. From the north pole we have our magnetic field line going in like this. Okay. So as you bring it closer, the number of field lines are increasing. So according to Lenz's law, the induced current should oppose that increase. That means it should try to decrease it. Decrease means the induced current should produce a new field that is opposite to the existing field. So that when the existing magnetic field due to the bar magnet was going in, we had to have the new field due to the induced current coming out like this. So that we need to look at the north here, and this is north. And so because it's the north, we have anti-clockwise direction. Okay. So now what have we produced? The induced current has now produced a north pole here. A north pole here. So that the north pole here and the bar magnet's north pole are going to repel. When they repel, if you need to bring it closer, you have to do work against that repulsion, and that work done is converted to this electrical energy. So it is under law of conservation of energy. This induced current, the new electrical energy did not appear from nowhere. As soon as this induced current, as soon as you try to bring your bar magnet closer, you will see that if you're bringing the north pole closer, you are now producing, a north pole is produced at this end of the coil, so that the two will repel each other, and you have to do work against that repulsion to push that bar magnet forward, and that work done is converted to the electrical energy, the induced current. Okay. In the similar manner, if you were trying to moving it away, the bar magnet is being moved away. Okay, you're taking a bar magnet away. Then that means the number of field lines are decreasing, because you are moving your bar magnet away from the coil. This is the north pole I'm talking about. So your field lines are going in, but you've pulled your bar magnet away. So the number of field lines here is decreasing. Now according to Lenz's law, the new induced current should, because there is a change in flux, as it is, you are pulling it back, the number of field lines are decreasing. So as it moves back, there is a change in flux which induces a current, and the induced current must flow in the clockwise direction, simply because when it flows in the clockwise direction, the new field produced will be like this, in the same direction, because this is south. Because this is clockwise would mean this is a south pole. Clockwise current would mean that this is a south pole, and therefore you will now increase the flux through the coil. I hope you understood that. As you move the bar magnet away, what are you doing to the flux here? You are reducing it. So induced current must try to increase it. That means it must produce a new field in the same direction as the existing field. So the existing field is like this. This new current should also produce a new field in the same direction, so that the net flux through the coil will increase. That means this is north and here you are south. So you're looking at the south pole. That means current is flowing in the clockwise direction. So here, now what happens is, this has produced the south pole. You will see that this is the south pole. S. Okay. Now so there is a south pole here facing the bar magnet, whose north end is facing that south pole. So there is naturally an attraction. So now if you want to pull the bar magnet away from the coil, you have to do work against that attraction, attractive force, and that work done against the attractive force is converted to the electrical energy in the induced current. So basically Lenz's law shows that this is under law of conservation of energy. You can't simply move a bar magnet close to a coil simply because and produce induced current or energy, electrical energy, simply because if you try to push your bar magnet with its north end towards the coil, it will also produce a north pole, which means there will be a repulsion, and to push it forward you have to do work against that repulsive force, and that work done is converted to electrical energy. Similarly, if you try to pull your bar magnet backwards, if this is a north end, immediately a south pole will be created because the induced current will now flow in the clockwise direction. So this south pole of the coil and the north pole of the bar magnet, there will be an attractive force. So you need to do work to pull it away from the coil. That work done has been converted to electrical energy in the coil as induced current. So Lenz's law shows you that this induced current is produced under law of conservation of energy. Now we move into motional EMF. Motional EMF. Here I am going to take a rectangular coil. Okay. Now this end of the rectangular bar, we have a bar, a rod PQ, which can move in and out of this rectangular frame. This distance I am going to call as X, and the length of the rod from here till here, the length of the rod taken from P to Q, I am going to call as L. And this is placed in a uniform magnetic field. Since I am showing you a cross, you should understand that the magnetic field is uniform, perpendicular to the area and inwards. Perpendicular to the area and inwards. Okay, so this rectangular frame has a bar which is free to move along the arms of the frame. The length of the conductor is L. This distance I will call as X, and the whole thing is placed in an external magnetic field which is perpendicular to the area and moving and inwards. Now if I try to push this bar to the left side, I am going to try and push this to the left. The moment I push it to the left, you will see that this area decreases, because as I push it to the left, here we see that the area enclosed will decrease. We know that flux phi is equal to NBA cos theta, and if there is a decrease in the area, there is a decrease in the flux. As soon as there is a change in flux, then there is an induced EMF given by d phi by dt with the negative sign, Lenz's law. Okay, so because of a induced EMF, there will be an induced current. Let's see in what direction this induced current is going to flow. So here we have pulled the conductor to the left side. The area is decreasing. There is a decrease in flux. So according to Lenz's law, the induced current should try to increase the flux, because the induced current should always oppose the change. And what is the change here? The flux is decreasing. So the new induced current must try to increase it, which means it should produce a new field in the same direction as the existing field, so that the two will add up and the flux will increase. So the new induced current should produce a new field in the same direction. Now because this was cross, we know that this is a south. So the induced current also should produce a south pole here, which means that it should flow in the clockwise direction. Okay, it should flow in the clockwise direction. I hope that is clear to you. So because you have pulled your rod inward, there is a decrease in the area, there is a decrease in the flux, and the induced current must flow in such a manner that it opposes this decrease in flux. That means it should try to increase the flux. If the flux should increase, it should produce more field lines in the same direction. So the external magnetic field, the already existing field we saw is cross, so that is south. So the new field produced by the induced current should also produce a south pole. So the induced current will flow in the clockwise direction. Okay, so that's the direction of the induced current. Let's find out the magnitude of this induced EMF E. So EMF E we know is minus d by dt of phi. Phi which is NBA cos theta. NBA cos theta. Now here we just have one turn here. So we will take n equal to 1. Theta I told you is the angle between B and A. Magnetic field we already know is perpendicular to the area and inwards. So we have our coil loop like this. Magnetic field is perpendicular and inwards. The clockwise current tells you that the area vector is perpendicular, and because it is clockwise current, the area vector is also inwards. So you will see that the magnetic field and the area vector both are in the same direction. So theta we take as 0. So that induced EMF now is minus d by dt of n is 1, cos 0 is 1. So we just have b into a, that is b into L into x. Since area of this rectangular frame is length into breadth, and this I have taken as x. Now as you move the rod in or out, you will see that you will only be changing x. L does not change. Length of the conductor remains the same. As I pull it in, it's only x that is decreasing. So I may take b and L both to be constants. So minus BL dx by dt. Dx by dt, displacement by time, is velocity, and we have our formula as minus BLV, where this B is the magnetic field intensity in Tesla, which is the number of field lines in unit area, perpendicular to unit area. L is the length of that rod which is moving in. V is the velocity with which it is moving. And the E is the induced EMF produced at the ends of the rod, between the ends of the rod. There is an induced EMF which produces an induced current in the clockwise direction, and that is represented by E in volt. Okay. Now we also have to show that this is under law of conservation of energy. So what we do is we go on to find out an expression for the current first. The current I, the induced current, I am going to denote with small letter I, because it is not due to any source voltage, any battery or cell. It is just the change in flux that has induced this current I in the rod, and that is what I am going to denote as small I. In current electricity, we had a source, a cell or a battery which produces current in a circuit, and that I represented with capital I. Here you see there is no battery, there is no source voltage, just the change in flux is inducing a current in the conductor, and that I am representing as small I, which is by Ohm's law, the EMF divided by the resistance of the coil or the rod. So I is equal to minus BLV by R, where this minus BLV we just derived. Now here this conductor is carrying current now, an induced current, and it is placed inside a magnetic field. You already learned in the 4th chapter that every current carrying conductor experiences a force given by the formula ILB sin theta, where theta is the angle between L and B. You will see that the length of the conductor is like this, and the magnetic field is an inward field, so that the length of the conductor and the magnetic field are perpendicular to each other, so that we may take theta as 90, sin 90 is 1. So then, this is small I that we are representing. So that the force experienced by this conductor, because it's carrying current and placed in a magnetic field, is equal to minus B, this is minus BLV, so this is minus B square L square V sin 90 is 1 divided by R, because I substituted for this as BLV by R, so that B and this B square L square V by R with a negative sign. Now so this force is a vector. Let us look at the direction of the force experienced. You know It is given by the Fleming's left hand rule. We'll check with Fleming's left hand rule, where this forefinger gives you the direction of the magnetic field. This is the current and this is the force experienced by the conductor. Now you will see we have the magnetic field into the conductor like this. The current is in this direction. So the forefinger pointing inwards because we have an inward field. The middle finger giving you the direction of current in the downward direction, and the thumb gives you the direction of force experienced. And so we have the force experienced in this direction. That is the force experience. So you will see that every time you try to move your conductor inwards to the left, immediately this conductor will carry an induced current, because of which it will experience a force to the right in the opposite direction. So which means if you need to push your conductor inwards, you have to do work against this opposing force, and that work done has been converted to this electrical energy. So this electrical energy didn't come from nowhere. It was not just created. It is because if you try to move the conductor to the left, immediately there is an induced current which will produce a force in the opposite direction, so that you will have to do work against that opposing force, and that work done has been converted to electrical energy. Okay, let us then look at the power here. Power is, as you know, F dot V from 11th standard. F dot V, where power is equal to FV cos 180 in this case, since you see that the force and the velocity are at an angle 180. So this is power is F dot V. Dot product is cos theta. So we have, I'm substituting for F from here, that is minus B square L square V by R into V into minus 1. Cos 180 is minus 1, because of which we have this as B square L square V square by R. B square L square V square by R. That's a formula for power. Now here, what is heat? Joules heating. Heat is always, power is work done by time, or this is power into time, whereas where heat is a work done, heat energy produced will be the work done. So heat is power into time, which is B square L square V square by R into T from here. Now Joules heating we know is, Joules heating in 10th standard you have learned the formula as I squared RT. This you have already learned in 10th standard. Joules heating, whenever current flows through a conductor of resistance R, it produces heat given by the formula I squared R. This is a formula given to you. So if I substitute this I here, then I will have I is, this is a formula I am going to substitute, square it, and you have B square L square V square by R square into RT. Cancel this R and this R, we have this as T and this will be R. You will see that these two formulas are the same. So what I am trying to tell you here is, this is all under law of conservation of energy. That is, as you try to move your conductor to the left, immediately the conductor will experience a force to the right because of the induced current, and you will have to do work against that force, and that work done has been converted to electrical energy. This electrical energy, as it flows through the conductor, heats up the conductor, and you will see that the formula for the energy produced is equal to the Joules heating formula. Same thing, B square L square V square by R into T. The Joules heating there also says B square L square V square by R into T. So the conversion has been, you have to do work against the repulsive force to move the conductor in the magnetic field. That work done is converted to electrical energy. The electrical energy that flows through the conductor will heat up the conductor, and the energy, heat energy also has, you will see, is under conservation. It's the same formula that you're getting. So this is how you can prove that motional EMF also follows law of conservation of energy. Now the same thing. So we have now just shown or derived an expression for motional EMF using Lenz's law. We have been using Lenz's law here. You can come to the same formula and same direction of induced current through Lorentz force, which we learned in the 4th chapter. Lorentz force, which is QVB sine theta, the force acting on a charged particle moving inside a magnetic field. So Lorentz force, I hope you remember. Lorentz force F equal to QVB sine theta, where theta is the angle between V and B, your charged particle of charge Q moving inside a magnetic field with a velocity V, and theta is the angle between V and B. That is magnetic Lorentz force on a charged particle inside a magnetic field. Using this, we may come to the same formula for motional EMF, BLV, and give the direction of the induced current also. So previously we used Lenz's law to arrive at that formula. Now we are going to use Lorentz force. Let's see how. So here we had this frame, rectangular frame with a rod PQ of length L. Rod PQ had length L. We placed it inside a uniform magnetic field like this. And we tried to move the rod to the left side. Okay, velocity to the left side. Now, when you move it to the left side, you have to do work, right? So, what happens here is, all the electrons in this conductor, as you move the rod to the left, is now starting to move to the left. So, all the free electrons in this conductor are moving to the left. And they are moving inside a magnetic field. So, they will experience a Lorentz force given by F is equal to QVB sine 90, because I told you theta is the angle between V and B. Velocity is like this. Along, let's say this is the x-axis, this is the y-axis, and this is the z-axis. Okay. So, we now see that it's moving towards the negative x-axis. And magnetic field is inwards, that is in the negative z-axis, inwards. I hope you understand what I am saying. I am taking this as the x-axis, this as a y-axis, and perpendicular to that we have the z-axis. So if you look at this diagram, V is towards the negative x-axis, B inwards and perpendicular to the plane, xy plane, and therefore we take it in the negative z-axis. So angle between V and B will be 90. So sine 90 is 1. So we have our force equal to QVB. Okay. Now let's see what happens to these electrons as they move to the left. They are experiencing a force. So if they are experiencing a force, they should start moving. Let's see in which direction this force is going to act. Now the vectors involved here are V cross B, because you know Q is a scalar quantity. So these are the vectors. Now, V we took towards the left, that is the negative x-axis. So, I am going to mark it as minus I cap cross. B is perpendicular and inwards. So, along the z-axis, inwards. So, therefore, I am going to take it as minus K cap. And I cross K has to be J. And I have always told you, if you take IJK like this, I cross K is in the clockwise direction. So, it will be minus J. So, minus J. This minus into minus is anyway positive. So, I will repeat again. You have I cross K. Minus into minus is plus. But I cross K is in the clockwise direction. So, this will now take a negative J. So, that means if it is a Q charge, that is positive charge, then those positive charges are going to experience a force in the negative y-axis. But we are having free electrons which are negatively charged. So the free electrons must move along the positive y-axis. Because when you get minus J, we are talking about force acting on positive Q. So if it had been positive charges, they would have all moved along the negative y-axis. But because we have free electrons in the conductor, Opposite to that, the free electrons are going to experience a force in the upward direction, that is positive y-axis plus j. So all your electrons are now going to experience a force in the upward direction like this. So what happens is the free electrons in this conductor are moving up. So they are getting removed from here. So that means this end becomes positive and this end becomes negative because they are being removed. Electrons are removed from here and being deposited here. So this end becomes positive and this end becomes negative. Now since your electrons are moving up like this, the direction opposite to movement of electrons is given as direction of current. So we say that the induced current is in this direction. That is what we got previously when we used Lenz's law also. We said that the current was moving in clockwise direction. Here the electrons are moving up. So direction of current is taken to be opposite and that means the induced current must be from P to Q, right? And that is what we got when we did Lenz's law also. Please note one thing. When you look at this, you will see that you have marked the current, the induced current I, moving from negative to positive. Whenever we did current electricity, the current capital I, we always took from moving from positive terminal of the battery to, see if you have a simple circuit like this, positive to negative. That is because this is the cause. Because of a potential difference, we have the effect is the movement of electrons and therefore current in the conductor. So cause is the potential difference. The effect is the current in the conductor. Here that's not how it is. Because you move the conductor in the magnetic field, the free electrons experienced a force and they were removed from Q. They experienced a force in the upward direction. They were removed from Q and deposited at P. So that this end became positive and this end became negative. So this is, you are now, the movement of electrons are now producing a potential difference which we call as induced EMF. I hope you have understood the difference. Here because of the movement of electrons, that is because of the induced current, we have a positive and a negative, an induced EMF across the conductor PQ. So movement of electrons, that is removing electrons from Q and depositing at P, electrons are moving in this direction. So induced current will be marked in this opposite direction. That means it will look like from negative to positive. Okay. Now, so we got the direction just like we got in Lenz's law. Let us look at the magnitude of this EMF. EMF which we know as B, EMF and potential difference. When we come to this, since there is no cell or battery, the EMF and V are the same. Remember in current electricity I told you, when you take a cell in a circuit, if the cell is in open circuit, then we call it as EMF. If the cell is in closed circuit and is carrying current, then we call it as V. But when you come here, there is no cell. So whether you use E or V, it doesn't matter. It will be the same value. So E or V, which is work done by Q. I hope you remember in the second chapter I taught you work done is equal to Q into V. Remember that. Okay. So work done by Q will be V, which is our EMF here. This work done is what? Force into displacement. The force into displacement by Q. Now what is the force experienced by this? Force is QVB. So we may write the EMF here is QVB. What is the displacement of this electron, the charge that it is experiencing a displacement? It has been displaced from Q to P, removed from Q and deposited at P. It's moving in this direction. So the total displacement is length of the rod divided by Q, and we get this as the original BLV. So in magnitude, we have the induced EMF. Using Lorentz force, we got it as BLV. In using Lenz's law also, we got it the same, BLV, magnitude. The direction of the induced current, whether we use Lenz's law or Lorentz force, we see that it is in the clockwise direction. So, whenever you get a question, be careful. Derive an expression for motional EMF. You have two ways. One, you can do it using Lenz's law, or you can Do it using Lorentz force F equal to QVT sin theta.